You ever wonder how your streaming service just knows what movie you'll love next? Or how a business can predict its sales months in advance? Well, a lot of the time, the secret behind that magic is a surprisingly simple yet incredibly powerful tool called linear regression. And today, we're going to pull back the curtain on this secret sauce of the data world.
I know what you might be thinking. A straight line? Predicting the future? It sounds way too simple, right? But that is precisely the magic we're going to dive into. We're going to see how this one basic idea can unlock some seriously powerful insights from all the data that's floating around us.
All right, so to really get this, let's start with a simple puzzle. This will get us right to the heart of the kind of problem that linear regression is just brilliant at solving. Okay, picture this. You have to guess a person's weight. The only piece of information you have is their height. Now, you've got a gut feeling, right? Taller people generally weigh more. But how do you turn that vague feeling into an actual number, a concrete, educated guess? That is the exact challenge we're going to tackle. So where do we start? Well, first things first, we need some data. We'd go out and collect the height and weight from a bunch of different people and just organize it in a simple table. So for each person, we connect our predictor, height, which we'll just call X, to the thing we're trying to predict, weight, which we'll call Y. So with our data in hand, the real quest begins. We need to find the one single straight line that does the best job of representing all those different data points. This is the hunt for the best fit. And yeah, this quest, it has an official name: linear regression. At its heart, that's all it is. It's a method for drawing the best possible straight line through all our scattered data, giving us a simple but really powerful model of the relationship between them. But what do we really mean by best? What makes a line the best fit? Well, it's the one unique line that manages to get closer to all of our real-world data points than any other line could, on average. It's the line that minimizes the overall error. And here's the really cool part: how we actually measure that closeness. There's this method called the sum of squared errors. Now, that sounds super complex, but the idea is actually beautiful. For each of our data points, we just measure the vertical distance to our line. That little gap, that's our error. Then we square those errors, which does two things: makes them all positive and gives more weight to the really big misses. And then we just add them all up. The best fit line is simply the one with the smallest possible total score. That's it. So now that we've found our winning line, let's pop the hood and see what actually makes this thing work. It's time to break down the blueprint of this predictive machine. Every straight line has to start somewhere, right? In our model, we call that the intercept. It's the value our line would predict for weight if a person's height were 0. Now, of course, a height of 0 isn't really possible, but think of this as the mathematical anchor point. It's crucial for getting our line positioned in just the right place. And next up is the slope. Now, this is the real engine of our model. You can think of it as the recipe for change. The slope tells us exactly how much we should expect the weight to increase for every single 1-inch increase in height. It perfectly captures the strength and direction of the relationship. And this is how it all comes together in one beautifully simple equation. Our predicted weight, Y, is just the intercept, our starting point, plus the slope, our recipe for change, multiplied by the height we know, X. And that little symbol at the end, that's just a little reminder that the real world is messy. It represents the error or noise that our perfect line can't quite predict. Okay, so we've built our line, which leads us to maybe the most important question of all. Is it any good? I mean, how much can we actually trust its predictions? It's time to find out how we grade our model. And for that, we look at this number, R squared. Think of it like a report card for our model. It tells us how well our line actually fits the data. So an R squared of 0.75 means our simple model, using just height, can explain about 75% of the variation we see in people's weight. The closer that number gets to 1, the better our model's grade. But for that report card to be meaningful, our data has to play by a few key rules. First, the relationship has to actually be linear. It should look more like a line than a curve. Second, our data points have to be independent. Third, the error should be pretty consistent. That's a fancy word, homoscedasticity, but it just means our model is just as good at predicting for tall people as it is for short people. And finally, those errors should be random. These rules make sure our model is reliable and not just a lucky guess. Okay, so predicting weight from height is a fantastic start, but the real world is a lot more complex, right? So what if we want to solve more complicated puzzles? Well,
This is where our simple line gets a serious power-up. Welcome to the world of multiple linear regression. Now, the core idea is exactly the same, but instead of using just one predictor, we can now use 2 or 3 or even dozens to make our predictions way more accurate. And the upgrade is surprisingly simple. We just start adding more variables to our equation. Each new factor we add gets its very own slope, its own unique recipe for change that contributes to the final prediction. Take a classic real-world example, predicting a house price. You wouldn't just use its square footage, would you? Of course not. You'd also want to add in the number of rooms, maybe a score for the location, the age of the house. Multiple regression lets us weigh the importance of all these things at once to make a much smarter, more nuanced prediction. And the great news is you don't have to do all this complicated math by hand. Powerful tools like Python with libraries like scikit-learn can build these sophisticated models in seconds. It makes all this predictive power accessible to pretty much anyone with a curious mind and a little bit of code. So we've seen how a simple line can be a profound tool for making sense of the world. But here's the final, crucial takeaway I want to leave you with. A computer can always find a line to fit your data. The real art, the real skill, is knowing when that line tells a true story and when it's just capturing random noise. The most important question you can ask isn't, can I fit a line to this data, but should I? And that right there is the difference between data analysis and data wisdom.